So the last thing in differential equations that we're going to talk about is a slope field. And before we get started on this, I want to talk a little bit about what a slope field is and what it looks like. So some of you guys are familiar with magnetic fields. And so basically whoops, that's not what I wanted. Basically, a magnetic field is a slope field. It's the rate of change everywhere. And so we can take this slope field and we can sketch this out from a function, right? So it's differential equations. We're talking about having a differential equation, so some rate of change everywhere. So where is this thing changing? Everywhere. And when we sketch this, we're not just sketching like the line x minus 1. We're sketching the rate of change at all these different points. And there's kind of a strategy to this to graph these things. And so we're going to graph the rates of change everywhere. We should come over and maybe make some labels on our graph. So let's go, I guess we'll go, let's do it like this. We'll go, so for x is 0, -1, -2, -3. And then we can go 1, 2, 3. There's no y values in this differential equation, so that's going to make our job a little bit easier. And so these ones are always kind of nice, right? So all we have is these x values. When we sketch this graph of the slope field, we need to kind of set a table up, right? So we have our x's, we have our y values, and we have our dy dx or our x minus 1 values. And so here's what we're going to do. We're just going to plug our x values in, and so we'll start from the smallest x value, go -3, -2, -1, 0, 1, 2, and 3. There are no y values, so that's pretty nice. And remember, this dy dx is equal to x minus 1. Well, this is the rate of change. So essentially what we're doing is we're going to evaluate this derivative at each one of these x coordinates, right? And so kind of earlier notation, dy dx evaluated. In this case, at x equals, we'd start with -3 and then go to -2 and then so on all the way down the line. So I'll just kind of write these first couple out. We're going to substitute our -3 in for x. So we get -3 minus 1. That's going to give me a -4. And we're going to do this all the way down. We're going to substitute -2 in for my x value and get -3. -1 minus 1 is -2. 0 minus 1 is -1. 1 minus 1 is 0. And 2 minus 1 is 1. 3 minus 1 is 2. So these values that we found, this is the rate of change at each one of these x values, right? We just found the rate of change. So let's come over here to, -3, x value of -3, and we're going to start sketching this in. Now, because there's no y values, at all of my x equals -3 values, this rate of change or the slope is going to be the same. So my slope is, whoops, that should have been a -4 right there. Make sure you fix that. Make sure you make that a negative. Sorry about that. So we come over to -3 and my slope's -4. So that means essentially we're going down 4 over 1, right? So that slope is going to be pretty steep. And that's our slope at all of those x values. When we go to -3, our slope is going to be, when we go to -3, our slope is, or -2, excuse me, our slope is -3. So we're going down 3 over 1. So it's a little bit less steep. A little bit less steep. And then when we get to -2, so when we get to -1, my slope is -2. So kind of like this. And when we get to 0, my slope is -1. So something's kind of happening right here. And then when we get to 1, my slope is 0. So there's like a horizontal tangent line there for our slope. When we get to 1, our slope is 1. So looks like a 1. And then when we get to 3, my slope is 2. So we're going up 2 to the right 1. Well, that should be a little steeper, I think. So about like that. And that's our slope field. Now, the kind of interesting thing about our slope field is we can look for like solutions for this slope field, and I want to talk about what's going on. This slope field like pushes things in a certain direction. So if you were to put your pencil like right here, and start tracing the slope field, it's going to, these slopes, right, these rates of change, you're following these rates of change around. And so you're going to end up with something like that. And my line's going to go away here in a second. So you're going to be asked at some point, you're going to be asked to like find a line, like graph the solution set at the point, and I'm just making this up, at the point. And so let's do one. No, let's do -2, 2. So -2, 2. So what that means, and this is important, right? When we come over to -2 and we're at 2, we're right here. So essentially that's where we're starting. So when we start tracing this, we're just following these lines of the slope, right? And this is not going to be like an exact science, but it should be pretty close. Now, a couple of things. If you stop like that, we need an arrow on the slope line, the slope field, at the end of that line. And so that's it. That is all that's going on. Now, if we were to look at this, the solution curve, right? It looks like our parent, like the original function was quadratic. And if we go back to our differential equation, if we were to like try and solve this differential equation, we'd move our dx over, we'd integrate, and then we'd end up with 1/2 x squared minus x plus c. And so that gives us that differential equation, that parabolic or quadratic shape. And the plus c would have something to do with how we're moving around over here. And so that is slope fields for example 1. Let's move on to example 2. So example 2, we don't have any x's, we only have y's. So we really only need to label our y values on this. I mean, we could label our x's too, but let's just label our y's. So start with 0, whoops, let's do something that's going to stay 0, 1, and 2, -1, and -2. And we're going to build our table the exact same way. So we'll have x's, and then we'll have y values, and then we're going to have our dy dx, or our y prime, whichever you want. And if you want, you could write in our 1/2 y here. That works as well. So just to kind of make sure we're on the same page. So there's no x's in my equation up here. So let's just scribble that out. We don't have to worry about x's, just y's. So let's start with our smallest y value. Let's start with -2. So we would do -2 times 1/2, and that gives me a -1. We'll do -1. So we times -1 times 1/2, and that is -1/2. We could do 0. So, and I probably should have been putting the parentheses the other way. It doesn't really matter. So we're going to do 0 times 1/2 is 0, and then we'll do 1 times 1/2 is going to be 1/2, and 2 times 1/2 is going to be 1. And so what we want to do now is kind of jump over here and sketch the graph. And I'm going to start at -2. I'm going to start down here at -2. We see when we're at -2, my slope at -2 is 1. So I come over here, and that looks about like that. Now remember, as we're moving on my x-axis, those x's aren't going to change, right? So the y value, the y value for all of these things is the exact same. So -2, all these slopes are -2. When we go to -1, my slope is -1/2, so it's a little bit not as steep. Down 1 to the right 2. When we get to 0, it's 0. These are horizontal tangent lines. I'm going to make it big, just like scribble a lot, just to make sure we can see. And these lines, we're not connecting these lines, right? These are all dotted lines because the slope is changing at each one of these points. When we go to a y value of 1, our slope's 1/2. So it looks like it's getting maybe about like that. And when we get to 2, our slope is 1, so a little steeper. Okay, so there's our slope field. And kind of something interesting is happening here, right? If we were to start like right here, like start at 0, this type of slope field, and you guys don't need to know this, it's just something interesting. If you go on to mathematics, you'll talk about this. We have what's called equilibriums. And so there are stable equilibriums and unstable equilibriums. This would be an unstable equilibrium. And so think about it. As we're moving this way, what's going to happen as soon as we move off of that axis just a tiny, tiny bit, we're going to either shoot up and we're never going to come back down, at least as far as we know. And if we're coming on this other side, the same thing's going to happen, right? As soon as we start to get off, it's going to stop, or not stop, but we're going to shoot down. And so this would be an unstable equilibrium. Now think about if our slopes of all these slopes were reversed, right? So it would be pushing us up into this equilibrium point of the x-axis, and then that would be a stable equilibrium. All right, our most interesting function, dy over dx is equal to x minus y. So we have x's and y's, and so we might want to go ahead and label everything over here right now. And instead of like labeling it on the axis, I'm going to label it out kind of outside the axis. So we go 0, 1, 2, 3, -1, -2, -3. And I'll do the same thing for the x's, 0, 1, and 2, and 1, -1, excuse me, and -2. There is definitely a strategy, and there's a whole lot of points. And so the kind of the main difference is, with our first two problems, we didn't have an x or we didn't have a y, so we didn't have to worry about all those points because they were going to be the same. And what I mean is, like in example 2, we didn't have the y, we didn't have x's, so the y values had all the same slope across that entire area, right? That slope is all the same. So it was pretty easy. We didn't have to do a whole lot of work. This one is not going to be quite so fun, but our strategy is going to be the same. We're going to start with an x, and we're going to draw our line all the way down. We're going to have a y, draw a line all the way down. And we know that this is going to be y prime or x minus y. And so the strategy that we want to do is we want to think about, like, to start. We could just start here and then go here and then go here and try and evaluate all those points. But that's kind of a pain in the rear end. So let's think about where the slope is 0. And so what that means is, like, if the slope is 0, right? So easy values, if we do 0 for y and 0 for x, 0 minus 0 is 0. So I know at this coordinate point, my slope, I'm going to switch over to red for here just to make sure we can kind of see it. Hopefully you can see that okay. My slope there is 0. And so then we would do, we could do this point 1, 1. And so we get 1 minus 1, that's 0. So my point 1, 1 is also 0. And we could just kind of keep going through there, right? We could do the point 2, 2, that's going to be 0. So we come over 1, 2, and up 2, that's 0. We could do, let's see, we could do the point, we want all these zeros, right? We could do -1 and do -1 and -1. So this is going to be -1 minus -1, so that's going to be 0. So we come over to -1, -1, and we get 0. We do the same thing, -2, -2. That would give us a -2 minus -2, which would also be 0. So at -2, we're at 0. And we could do, and so that's it. So we're kind of working our way in, right? We're kind of working our way in. The next thing that we would probably want to do is let's just make a little note. This was where the slope equals 0. And so the next thing that we would want to do to try and graph this whole thing is we would probably, we could either look at just the x-axis or just the y-axis, right? And so we could kind of look at slopes on the x-axis. If we're looking at these slopes on the x-axis, we'd start with -3, 0. So we do -3, I'm going to draw a line right there just to separate it out, -3, 0. So we get -3 minus 0, that's -3. So when I come over here to -3, 0, so that's our slope, is going to be pretty steep down, right? We're going, down 3 over 1. So our slope is going to be pretty steep negative. Then I would go to -2, 0, -2, 0. That's going to give me a slope of -2. So it's not quite as steep. -1, 0. -1, 0 is about like that. We already did zeros. We already did 0, 0. So we don't need to repeat that one. So let's go to 1, 0. So we do 1, 0, and that would be 1 minus 0 is 1. Let me erase that little tick mark. That would be 1. So now our slope is looking like that. We would do 2, 0. That's going to give us a 2, so steeper. And then finally 3, 0 would be a 3, and that's going to be very steep. So we did the x-axis. We did the places where it's equal to 0, the slope is equal to 0. I want to pause the video, and I want you to do the y-axis, and then start the video, and we'll talk about what's next. All right, so we found the points on the y-axis, and I've got that right here. We sketched those in. We have all of these other points that we need to sketch in, right? We need to get slope fields for all of these other points. And so at this point, what you're going to do is you're just going to go figure out these slopes for all these individual points and write them in there. And you're just going to like do your best, right? It's kind of tedious, but I'll let you go. I'm going to pause the video. I'm going to fill the table out, start the video, and see where you're at. So this is what I got for my slope field. And we can draw our solution curve, and we could pick different points and just kind of plug things in, right? Like if we were to start up here, it would look like that. And if we were to start down here, like maybe over here, it would kind of go this way, and then it's going to curve up like that. So we could do more solution curves, right? Move in here. This is kind of a weird function. And it makes sense that this is kind of a weird function. If we were to like somehow take the derivative of that, it would end up being implicit. And so it sounds like, or it looks like maybe our original function was not a function. And so this is slope fields. Hope you liked it.